So chi-square is another topic like binomial expansion where there's a lot of math, but you also have to understand a lot of conceptual stuff. So we're going to go through it all, and hopefully you have a good grasp on it by the end. Okay, so first, let's talk about why we even use chi-squared. So if a family were to have 4 kids, what would you expect them to have? Well, you would probably say, I expect that they would have 2 girls and 2 boys because you know the probabilities of having kids, and that's what you would expect. But let's say that I tell you that they actually have 4 girls, or they have 4 boys, or they have 3 girls and 1 boy. I'm sure we've all met a family with that demographic in their kids. And it doesn't sound that crazy to us because we know that it's just due to chance. Whichever sperm happened to win the race. That's how you know you had 4 girls or 4 boys or 3 girls and 1 boy. And we just understand that in our head, like being a girl or a boy, it's just due to chance. We expect 2 and 2, but if it's a little off, it's like, it's chance. But what if a couple had 40 kids? What would we expect? Okay, well, obviously, we would expect half and half since the probability of being a boy and girl is the same. So we'd expect 20 and 20. Okay, so let's say they had 23 girls and 17 boys. Do you think that's due to chance? Well, probably. The numbers are pretty close. They're only 3 off from their expected value. So, yeah, it's just that a couple extra girl sperm happened to win the race, but that's just chance. That's how it works. You wouldn't really be that surprised by saying, oh, out of 40 kids, 23 were girls and 17 were boys. But let's say instead that the couple had 1 girl and 39 boys. Do you think that this is due to chance? Well, probably not. It's just way too far from normal. So those are each 19 apart from their respective expected value. And we would think, okay, maybe there's something else going on, like the husband not having any or barely having any sperm with an X chromosome. And that's why there's only 1 girl and so many boys. So it can be really easy to tell with people sometimes when something is due to chance and when it's not. Like 39 boys and 1 girl, yeah, that's not due to chance. There's something else happening. But 17 boys and 23 girls, yeah, that's due to chance. But sometimes it's not that clear with people or even just other organisms in general. So, like, is 27 girls and 13 boys due to chance? Well, that's 7 away from what we want. Is that due to chance? Is it not? It's kind of hard to tell. So we need to try and find a way to find out if the offspring ratio that we're given is due to chance or not. And chi-square is an equation that will tell us if the ratio is due to chance. So let's go ahead and talk about this formula. This is the formula in that little circle that we're going to be using. And obviously there's a lot of parts to it. It's very mathy, but let's break it down. So first, this right here is chi-squared. It's a squared value, but you're not trying to just solve for that x. You're actually solving for x squared, chi-squared, which means that you never need to take the square root of anything. So don't make that a mistake. You do not have to take a square root. Okay, so now let's talk about this weird looking E symbol right here. This is a Greek letter. It's called sigma, and it means the sum of. So we would have the sum of every single observed minus expected divided by expected, or squared divided by expected value. So for example, you would have an observed amount of girls minus an expected number of girls squared divided by the expected number of girls. You'd also have an observed number of boys minus the expected number of boys squared divided by the expected number of boys. Both of those would give you some numbers and you would add those two together. So that's what this sum means. So each of these, this is like a per phenotype. So like boy is a phenotype, girl is a phenotype, red eyes would be a phenotype, and so on. So you would just do it individually for each phenotype and then add the stuff together. And this will make a little more sense when we do our example too. So O, as I already kind of said, is your observed value. This is what actually happened. So in our example, we were talking about with the 27 girls and 13 boys, those are the observed values. That's what they actually had. That's what we saw. And your E is going to be your expected value. it's what you expect to happen. And a lot of times you're going to have to calculate this whenever you're given a chi-square value. So for us, in our example of having 40 kids, our expected values were 20 boys and 20 girls. But how did we actually solve that? What we did is we took our total number of offspring and multiplied that by the probability of a certain phenotype. So for example, we expect that half of them are going to be girls. We do 40 times 1/2 to get 20. So that's the formula. Now let's think a little bit about what the results would look like. If this O and E are pretty close together, that means when we subtract them and square, it's going to be a smaller number. And if the O and E are really far apart and we subtract and square them, that means that you would get a bigger number. So the bigger the O and E are apart from each other, that means we're going to get a bigger chi-square value. And the bigger chi-square value you have, the more likely the results are not due to chance. So smaller chi-square value means it's more likely due to chance. That would be like having your observed and expected really close to each other, like having the 17 and 23 versus the 20 and 20. And if the numbers are really off, such as having 39 boys observed instead of the expected 20, or one girl versus the expected 20, it's probably not due to chance. There's probably something else going on there. But how do we know what a big and small number is? We already know that bigger number or bigger difference between E and O, we have a bigger chi-square value. That means it's not due to chance. But what is a big and small number? This is where a p-value chart is going to come in. And there's two ways you're going to want to read this, but the most important thing is to remember that your 0.05 column is the most important column. That's what you're going to be focusing on. So there's two things you need to know. And this will make a little more sense too when we look at the actual p-value chart. A chi-square value larger than the 0.05 chi-square value means not due to chance. And a p-value smaller than 0.05 means not due to chance. So if you want something to not be due to chance, you either want a chi-square value that's bigger than the value we're looking at or a p-value smaller than 0.05. And just so you know what a p-value is the probability that it is due to chance. So like the p-value of 0.05 means that it's a 5% probability that it is due to chance. And that means that it's a 95% probability that it's not due to chance. And obviously, if it's a 95 probability not due to chance, it's probably not due to chance. So let's go ahead and look at our p-value chart. So this is the p-value chart off to the side. There's a couple things I want you to notice here. First, your degrees of freedom. Your degrees of freedom is going to be the number of phenotypes you're given minus 1. So for example, if you had boys and girls, that's 2 phenotypes, minus 1 would be 1 degree of freedom. And in this example right here, if you had 3 phenotypes, blue eyes, red eyes, and green eyes, that's 3, minus 1 is 2 degrees of freedom. All right, let's keep looking at the chart. So this big section in the middle right here, those are all your chi-squared values. So you'll calculate for a chi-squared value, and while you probably won't see the exact number here, you'll kind of see where it'll fall. And something I want you to notice about them is that they increase as you go from left to right. No matter what row you look at, they're going to increase. And this is what we talked about with bigger chi-square value means it's more likely not due to chance. And notice, as your chi-square value increases, your p-value is actually going to decrease. So that's why over here, if your chi-square value is bigger or your p-value is smaller, that's going to mean it's not due to chance. So they have that inverse relationship because of the way it is on the chart. As chi-square increases, your p-value decreases. Okay, so now let's talk about how to read the chart. So I told you there were 2 ways. The first way is to focus on your chi-squared value. The second way is to focus on your p-value. So I'm going to go ahead and first highlight our very, very important row, our 0.05, just kind of all the way down. Okay, that is going to be where we want to look every single time. That's going to tell us, is it a big or small number, was our question earlier. And so for this example with the eye colors, we have 2 degrees of freedom. So I'm going to come over to my 2 degrees of freedom, and I'm only looking in that row. So I'm going to give you a couple examples of what to do. So the first way to read the chart is to just look at the chi-square value. So let's say that my chi-square value, I got 3.8. So what I'm going to do is find my degrees of freedom, go over to 0.05, and see what that number is. So right here, you'll see it's 5.99. So that's my number that at that point and larger, we are not due to chance. 3.8 isn't quite big enough yet. We haven't made it to 5.99. So since 3.8 is less than 5.99, that means that it's likely due to chance. However, if, for example, I had the number 6, that would be bigger than 5.9, which means not due to chance. So if a question literally just asks you, is it due to chance or is it not due to chance, this is what you can do. Find your degrees of freedom, go over to 0.05, see that chi-squared value, calculate yours. If it's bigger, not due to chance. If it's smaller, due to chance. And that's pretty easy. The other thing that might happen in a problem is that they're going to say, what is the probability that it is due to chance? So this is where you're going to be looking more at your p-values. So let's go to our 3.8 example again. Oops. Sorry, 1 second. Okay. So looking at our 3.8 value again, what we're going to do is we're going to look in this row of number 2 and find where 3.8 would fit in. So it would fit in right here between 2.77 and 4.61. So once you find where it fits, you're going to go up to the p-value and see what it's between. It's between 0.1 and 0.25, which means that for 3.8, there is a 10 to 25% probability that it is due to chance. So those are your 2 ways to read it. First way is just for, is it due to chance, is it not? Compare your chi-square value with that 0.05 chi-square value. And for the second way, you're looking at the p-values. You're going to find your chi-square value, see where it falls between which 2 numbers, looking at your degrees of freedom. Go up to the p-values and then say, okay, it's between 10 and 25%, or if it was somewhere else, like if it was between the 90 and the 95, between 90 and 95% due to chance. So that's how we read the chart. Let's do an example now. So red ladybugs are dominant to green ladybugs. 2 heterozygote ladybugs are crossed and they have the following offspring: 300 red ladybugs and 128 green ladybugs. Are these results due to chance? So this question right here, are these results due to chance, or the question saying something like, what's the probability these results are due to chance? Those are super obvious question stems that are like, yep, I'm doing a chi-square problem. And there's not really a lot of ambiguity there, so you should always know if you're doing a chi-square problem. So let's go ahead and dive in. So first, I'm going to say that my red is dominant, and I'm going to label that big R. And my green is recessive, which is going to be little r. And I cross 2 heterozygotes. So I cross big R, little r, and big R, little r. And in my results, all I give you is like red and green, which are phenotypes. So I'm not going to worry about the genotype ratio. All I need is the phenotype ratio. This would be 3/4 the dominant, 1/4 the recessive, aka 3/4 red, 1/4 green. Okay, so now let's go ahead and dive into my chi-squared value. So I know that my formula is the sum of observed minus expected squared divided by expected. Let's figure out what all of these are. So for my red, my observed is 300. Your observed is always just what's given into you in the problem. And for my green, my observed is 128. So now we need to calculate our expected. To calculate your expected, you have to first find the total. So for expected, we have to do 300 plus 128, which is 428, is our total. And then we have to multiply those by their respective probabilities. So we would do 428 times 3/4, since 3/4 are going to have the dominant phenotype, which we knew from up here. And for our expected for greens, 428 again, times 1/4. Let me see what those numbers are. 428 times 3/4 gives you 321, and 428 times 1/4 gives you 107. So those are our expected values. Okay, let's plug it in. So remember, you're going to have an observed minus expected squared over expected for each phenotype. So I'm going to do red plus green. So for red, I want to do an observed minus expected squared over expected. And for green, I'm going to do an observed minus expected squared over expected. Let's plug numbers in. So for red, I would do 300 minus 321 squared divided by 321. And for my green, now I go to my green numbers, which is 128 minus 107 squared divided by 107. And we're going to add those together. Let's see what that is. All right. So for this first one over here, I got 1.37. And then for the second one, I got 4.12. And if you add those together, you get 5.49. And that's equal to our chi-squared value. So woo, we found our chi-squared value. And now we have to go to our p-chart because that's how we're actually going to determine if it's due to chance. So I'm going to lead you through both ways of solving. This question just wants, is it due to chance or not? So for this one, all you have to do is compare the chi-squared value to the 0.05 chi-squared value for your degrees of freedom. But I'm also going to show you how to find the percents just in case you're asked that. So let's figure out what our degrees of freedom actually are. So in this we have, so remember you count phenotypes. So we have red and we have green. And for degrees of freedom, you take away 1. So our degrees of freedom for this one is 1. 2 minus 1 is 1. So let's go back to our chart. I'm going to go over to 1 degree of freedom, and I'm going to find what that chi-squared value is, 3.84. So my 0.05 value is 3.84. So that means that 3.84 and bigger means not due to chance. And I got 5.49. That made it way past 3.84, which means that we are not due to chance. Okay, and let's see where our number falls. So we got 5.49. So if it asks like, what's the probability it's due to chance? I'm still in 1 degree of freedom and I try and find where does 5.49 fit? You would see it fits right here between 3.84 and 6.63. So that means that I have, this is between a 1 and 5% chance, probability due to chance. So there is a 1 to 5% probability that it is due to chance. which would mean a 95 to 99% probability not due to chance. So this is how you do your chi-square. I know it's a lot, there's a lot of math, there's a lot of conceptual, but it's really important that you get it down. So make sure that you practice with it, practice reading that p-value chart because it can be confusing if it's the first time you see it. And good luck.
I hope you found this video really helpful. The concepts and information presented in these videos will be true no matter what genetics class you are taking. However, the concepts presented in this video are referencing material currently covered in Baylor University's coursework. Remember, if you are currently enrolled as a Baylor student, we offer free tutoring services. Our tutoring center is located on the first floor of the Sid Richardson building. You will find all the details you need to know about these services on our website, www.baylor.edu/tutoring. You may schedule a free 30-minute one-on-one tutoring session online through Navigate, or just drop in during our open business hours. For more information about our current services, please visit our website. Thank you.